Well, hello and welcome to this power supply review for the AWSOM unit, a well system for ongoing maintenance. The aim is to look at the solar cells that supply the power and the power consumption of the various modules, and to determine the best way to supply the voltages and the currents that these modules require. Well, this is the circuit diagram of the AWSOM unit. It looks at the batteries, the current design batteries, the 4.8 volt nickel metal hydride batteries, can't use lithium, and the two 6 volt solar cells, 600 milliwatt each, supplying a small 100 milliamp 5 volt regulator for the Arduinos and the 4.1 volt boost buck regulator module from eBay, which supplies the power hungry and quite erratic SIM 800 unit texting unit. That unit takes a couple of amps for several hundred milliseconds, just a few hundred milliseconds after it has been turned on, and then it settles down to a manageable 100 or so milliamps thereafter. Everything else is relatively small amounts of power, but let's go through it piece by piece. Okay, the two solar cells are 60 millimeters by 90 millimeters and are both rated at 100 milliamps each. That's in bright, sharp shadowed sun. In Tanzania, I should imagine the sun is a little bit brighter than it is in UK. It's a bit more powerful, a little bit more ultraviolet, which obviously drives the output voltage higher. I have seen 7.2 volts from the 6 volt cells in sunshine in UK, and so just be careful when it says 6 volts, it's nominal 6 volts. The Arduino will work down to 4.5 volts. I've used it occasionally at 4.3. It works acceptably, but obviously it can't be designed that way. The SIM unit is voltage sensitive. It needs 4.1 volts, a couple of amps for several milliseconds after it's been started up. The Arduino is easily reset with a few hundred millivolts dip on its voltage lines, so this is going to be carefully looked at. The Zener diodes in the diagram are not for voltage regulation, they are just for protecting the voltages on the pins of the Arduino and the SIM unit, as we do not want to exceed the stated voltages on these items. Schottky diodes are used throughout due to their low forward voltage drop being about 300 millivolts. The 5 volt 3-pin regulator has a low dropout, also of about 300 millivolts, which works really well. The nickel metal hydride battery has spirally wound construction, so its structure finds it difficult to supply large spikes instantaneously. The relay switches not only the SIM unit on in the evening, but also turns the solar cells off from charging the battery when the voltages are too high. In this particular case, it is not deemed necessary to fully charge the batteries. As long as they're 60 or 70%, that's fine. We don't want pushing it to 100%. There's no need, and it's not necessary. Apparently, the battery can be trickle charged at a very low rate for months, but deep cycling is recommended every few months to maintain battery condition. Now, whether this happens in the field is unlikely, unknown, but it should be recommended at this stage. This slide highlights the main voltages required, which are 5 volts and 4.1, and the voltages available, 0 to 7.2 volts from the 6 volt solar cells, and a nominal 4.8 volts from the nickel metal hydride batteries. However, I've found that the 4.8 volts from the batteries is normally higher because we're not taking anything appreciable from it. In fact, it takes 70 milliamp hours during any 24-hour periods. That's made up of 60 milliampere hours during the day and 9 milliampere hours during the night. Yeah. The aim here was to trickle charge the nickel metal hydride batteries. Now, it's not recommended we do this, but I can't see any other way around it at the moment. The recommended trickle charge rate is about 0.05 C. Now, we're using 4 ampere hour batteries, so that equals to 200 milliamps. However, the solar cells can only give 200 milliamps total. That's 100 milliamps each, and that's in bright sunlight. So it's doubtful that they'll ever reach their maximum trickle charge. Yes. But without 6 volts, if you went down to 5.5 volts, the battery would never even reach 13 or 15, 20% of its total charge. So it has to be targeted at 6 volt solar cells. There's asymptotic charging techniques anyway, so it would never get there if it was 5.5, but the 6 generally keep it quite well stocked. Right. Okay, there we go. Charging at 95 milliamps, and I'm going to short that shock key out, which should go up to 120 something. I can't show you because I'm using 2 hands. Oh, there we are, look at that, 126. So 126 with that shock key shorted out, and with it in, 96. So that's 25%. Now, this was just a test for removing the series shock key diode, just increasing the target voltage by 300 millivolts increases the charge current by 30% to 25%, somewhere around there, as you can see on the screen. Yeah, but even so, it's not recommended to go
so 126
more than 200 milliamps, and we're approaching that, so I don't think we should do this.
96.
Well, this is just to test a relatively fresh battery. It's maybe a week, 2 weeks old, in the sharp shadowed sun from the old Huntington solar cells, and it's pumping out 130 milliamps, 120 milliamps, which is twice as much as it was when the sky was cloudy, but there's not a cloud in the sky. So ultraviolet's getting there, so that's where the energy is. So, out of all this, the questions are: how best to obtain 5 volts of the Arduino, and the 4.1 volts 2 amp peak for the SIM texting module. What voltage solar cells are recommended in the light of all the stuff that we know about now? And how will the batteries fare under the proposed trickle charge rate with the target voltage of 6 volts? How will the unit revive after a flat battery event, for example a year or more in the shack or on the shelf, which happens quite a lot? And what is the simplest and cheapest to manufacture solution for small batches of the circuit on the right hand side? And should we use 4.8 volts? Should we go to 7.2 and with all the benefits and drawbacks of that? Or should we go lower voltages and use a boost buck regulator for the whole thing? I don't think we can afford the current. It'll be about 18 milliamps 24 hours a day. But anyway, all this is up for grabs in the power supply and power and voltage considerations of the unit. Thanks a lot for listening.